Hello and welcome to Lecture 12. I'm Chris Mack, and we're going to play around with Excel a little bit today and generate some normal probability plots. To do this, I've set up some data already in this Excel file, which you can download from the course website. And the first set of data I'm going to analyze is a set of data where I already know the answer. Here's what I did. I created a set of 200 numbers that I pulled from a normal distribution. In Excel, you do that with this function right here. First, rand parentheses creates a random number uniformly distributed between 0 and 1. Well, probabilities are uniformly distributed between 0 and 1. So what I'll do now, well, not uniformly distributed, but probabilities always go between 0 and 1. So to turn a uniform probability into, say, a normal probability, I'll simply use the inverse normal function. So norm.s.inverse is the inverse standard normal distribution. If I give it a random number as its input, it will give me a random number from a normal distribution as the output. So I did that 200 times, and I created 200 random numbers coming from a normal distribution, a mean of 0 and a standard deviation of 1. Those are in the results column right here. Then I rank ordered them from smallest to largest. So here, this is the biggest negative number. All the way down to the bottom, I have the largest positive number. So I rank ordered them. When we do normal probability plots, that's the first thing we do. Then I numbered them. So the first data point is number 1, all the way on down to number 200. So I create a column, order number. That's the beginning. That's the data. That's the input. What I'm going to do next is use that rank order, K, to create an empirical CDF, cumulative distribution function, which we'll call UK. Our approximate uniform order statistic. Now, as we saw in the lectures, there's several different ways of creating that, and some at UK, and there's different approaches that different people have used. They're all about the same as long as n is reasonably large. And 200 is large enough. So basically, all the different techniques give you about the same answer if you have 200 data points. The one I use is the one I like the best. It's Phillipines Approach from a 1975 paper. Right, here's the full reference there for you to look at. But I'll go through kind of exactly how I do that. And I'll start with the last data point. For k equal to n, here's the formula. UK equals 0.5 to the power of 1 over n. So I go down to the very last data point there. And I say its value is 0.5 to the power of 1 over the last k, which is 200. So 1 over this number. And you see I get a number that's very close to 1. I don't want a number that goes all the way to 1 because in a cumulative distribution function, in a normal distribution, the only way to get to 100% to 1 is to have an infinite amount of data, infinite range of data. And since I don't, and in fact, I don't really want my numbers to go to infinity, this number ends up being a little bit less than 1. But you see it's pretty close to 1 if I have 200 data points. Now, that's the last number. The first number is 1 minus the last number. So UK for k equal to 1, simply 1 minus that last data point. That makes it symmetric. In between, see in row 10 here, for k equals 2, I'm using the formula for everything else. All the other data points from 2 to n minus 1, this is the formula I use. So that's obviously very easy to generate that column. This is an empirical cumulative distribution function. Then, assuming that the distribution is normal, I could assume something else. Whatever distribution I assume, I take the inverse of the CDF. Here I'm going to do norm.s.inverse because I'm going to assume it's a normal. So I take the inverse, and I took the inverse assuming a standard normal, that is a mean of 0 and a standard deviation of 1. I don't have to have a distribution that have those mean properties. and standard deviation properties. So once I've inverted it, assuming a standard normal, I then take that value right here, D9, I multiply it by the standard deviation from the data, which is here, B6, and add to it mean of the data. That converts it into an expected result. I do that for every single one of these data points. I now have a set of actual results and expected results, assuming that a normal distribution was correct. I also plot a slope equal 1, y equals x line as the dotted line, and that's this dotted line here in the graph. Okay. Well, this is the plot of that data, and the open circles represent the expected result that I've calculated assuming a normal distribution versus the actual result, which is the actual data. And if they fall along this y equals x line, then I did a pretty good job of guessing what the distribution really was. Now in this case, I made up the data as being from a normal distribution, so I certainly would expect it to fall along this line, and it does. Right? It's approximately true. And these variations are very typical because it is a random number. There's random variation to be expected. Notice that most of the data points lie near the mean, and as you'd expect, and out here at the tails, the extreme values are less frequent. So you see they're getting further and further apart out here at the extremes, and they're really bunched up together here in the middle, which is exactly what you'd expect. So here's an example where everything works out about what you'd expect it to be. But how close is it? Is this a really good fit or a sort of okay fit? Well, as we said in the lectures, we can figure that out using the correlation coefficient. So here I'm using Excel's function correl, which calculates the correlation coefficient. I have two columns of data. B is the the actual results, and E is the expected results calculated in the way that I've just shown you. I've performed the correlation and I get 0.9967. If it were perfect, I get a correlation of 1, and so the fact that this is very close to 1 makes me think that the assumption of a normal distribution is valid. But we can do more than just think that. We can actually do a statistical test. Again, as we mentioned in the lecture, there's a critical value for the correlation coefficient given a certain significance level and a certain number of data points. And as long as this correlation coefficient I get from the normal probability plot is above that critical level, I can't reject the null hypothesis that the distribution really is normal. So the last tab of this spreadsheet shows those tables of critical correlation levels. So the first table shows different significance levels from 0.05 all the way up to 0.1 and number of data points from 3 to 100. The second table only has significance levels of 0.01 and 0.05. Those are the most common that people use. But its table goes up to n of 1,000. So if you have larger than 100 data points, then you want to use this second table. Let's look up. We have 200 data points in this particular data set. So here it is. With a significance level of 0.01 and a significance level of 0.05, we see that the critical correlation coefficients are about 0.99 and about 0.993 respectively. And what was our number? It was 0.997. So the correlation coefficient we got was above the critical correlation coefficient, regardless of which significance level that I chose. And as a result, I can't reject the null hypothesis that the distribution really is normal. Well, that's kind of what I expected because I actually did generate normal data. But, you know, sometimes it fails because of randomness, right? These are all probabilities, not certainties. All right, that's kind of a fake data set. Also perform the same analysis on some real data. Here's the data that I got from dataset 1, which is on the website. univariate data. It's a kind of an interesting test where these two guys, actually I don't know if they're both guys, two researchers, Ambler and Jones, of the National Bureau of Standards, now it's called NIST in DC, made 100 measurements of a standardized weight. Now, NIST is in the business of calibrating measurements and creating standards, and they created a standard that was 10 grams. And then they did this test. They took this 10-gram weight, approximately 10 grams, and they weighed it once a week for 100 weeks. In between, they stored it very carefully, preserving the quality of the artifact. And every week they took it out and they used their best measurement procedures to get a weight. Then they recorded the numbers, and here we have those numbers. Actually, what we are plotting here, or showing here as the result, is the difference between measurement and 10 grams, expressed in milligrams. So here, the result is 375, the first result. That means the actual weight they got was 10.375 grams. I have these 100 data points. I then rank ordered them. So I ordered them from the smallest to the largest and gave it a trial number, 1, 2, 3, etc. Now we're going to go through and perform our typical normal probability plot generation. Our UKs, the empirical CDF, is generated using those same formulas I mentioned just previously. And once I have those, I'm going to assume a normal distribution and take the inverse CDF. I will convert that to an expected result by multiplying that number by the standard deviation from the data, here at 6.5 milligrams, and adding to it the mean of the data, 404.6 milligrams. That gives me an expected result, which I can plot compared to the actual result. Here's the graph. What do we see? The dotted line, again, is y equals x, which is what we'd expect if it truly was normally distributed. What we see here for this actual data is heavy tails. Right? Just like we talked about in the lecture, we see some distribution that curves up at the top and curves down towards the bottom. If I expected a value of, say, 420, right about here, what I actually get is a number bigger than 420. Right? So the numbers go above the dotted line at the extreme values, and they go below the dotted line at the extreme values on the other side. If I was expecting 385, what I really got was 375. More extreme than I expected. When numbers are more extreme than you expect, that means heavy tails. So here I see a distribution that looks to me like it's not exactly normal. I could test the correlation coefficient. Notice the correlation coefficient is quite a bit lower than it was last time, 0.906. If I go to the critical correlation numbers and I go down to n equal to 100, you see that for all of the different significance levels, all the correlation coefficients are much bigger than 0.90. So if we can reject the null hypothesis that this data is normally distributed. And you can see it's from the heavy tails. Now, just for fun, can you really see that from the from the histogram? I don't know. The histogram doesn't show you nearly as much detail as you get here. So I think this normal probability plot is much more useful for testing the distribution than a histogram would be. As I showed you in the lectures, you can look at light tails, and we'll see what that looks like here. I happen to generate a uniform distribution of numbers, random numbers, and compared it to a normal distribution and showed that the uniform distribution has much lighter tails, as of course you would expect. right skewed, left skewed. We can definitely see these different shapes. And if you want, you can go and look at these spreadsheets and see exactly how I generated these data and how it plotted. Of course, the way in which I generated the empirical CDFs and inverse expected results is exactly the same for all of these. All right, so that's lecture 12 in how to generate a normal probability plot. I'll leave you by switching very quickly to a second spreadsheet, 12b, and show that the same technique can be used to compare not the expected value compared to the actual value, but the empirical CDF compared to what you expect over the unassumed or reference CDF. So just like before, we calculated UK, which is our empirical CDF. This time, I'm going to plot that empirical CDF versus the actual result. So these circles here is column B versus column C. It is the empirical CDF versus the result. Then, on the same graph, I can plot a curve of a normal distribution or any distribution I might want to see how well it fits. So here I can more directly compare an assumed CDF relative to the empirical CDF. And so in this case, I'm assuming I've got a normal distribution. Plot the normal distribution as the black line here, the CDF of a normal distribution, plotted right alongside the empirical CDF. And they match up pretty well, as you'd expect. Maybe the more interesting case was this Ambler and Jones set of data. Remember, we saw it had heavy tails. If I plot the empirical CDF versus the actual result, I get the round circles here. Then in the black, I'm doing two things. I'm plotting a normal distribution. But I'm not plotting it with the same value of standard deviation. So if I were to plot this assumed normal distribution using 6.5 nanometers as the standard deviation, which is the standard deviation I get from the data, then here's the matchup, the comparison between the empirical CDF and reference, or the assumed probability distribution. You see it's not a very good match. It's not a very good match because of those heavy tails. But that was based on my estimate of the standard deviation. That was just the normal formula. In fact, you can take a look at my formula. Standard deviation STDEV.S, a sample standard deviation formula for all the data. But if I were to adjust the standard deviation downward, I can get a better fit, better match. This is in fact just a different way of estimating the standard deviation, one that tries to get the best fit of the empirical CDF compared to the assumed CDF. Of course, the real issue here is that we have heavier tails than a normal distribution, but it just goes to show you that those heavy tails are throwing off my calculation of the standard deviation. This is not the best standard deviation that matches this data set if the data set truly were normally distributed. That is, of course, a good estimate of the standard deviation for heavy-tailed distribution, not for a normal distribution. All right, so you can look through the other tabs on this to see exactly how I did the same kinds of things, but useful for determining what kind of distribution you think might best fit the data by plotting it in this fashion. All right, that's Lecture 12. Thanks until next time.